come back to our 2 square design. So this is the general expression, right? Y naught, y equals q0 plus qa and so on. So if you look at those 4 values for each of the rows, that's y1, y2, y3, y4 and so on, right? So I can express yi in terms of the corresponding xai and xbi, right? So xbi, this will be -1 plus 1 minus 1 plus 1 depending on which row that you are currently looking at. So this is a generic form for yi, right? So since you are all asking me that we should prove why that SST expression was correct, so let us go through the proof for that and then it is mostly miscellany after that, okay. So some observations, right, we saw this earlier too, right. If you look at xai across all the 4 rows, right, what is that summation equal to? Sorry, this is across a column, right. So for across all the 4 rows in a given column, right, what do all the xai's add to? 0, and so does xbi also add up to 0, right. And the xai bi column also adds up to 0, right. That is observation from the table. And if I add up the squares, if I square up each number, not that 4, is 4, okay. Then how about the dot product of any 2 columns except that I column? If you look at column A and B, right, then what is the dot product? Okay. So likewise ai into that ai bi column is also 0. So all the corresponding column products, right, go to 0. Okay. So if I look at the sample mean, which is simply 1 over 4 all the yi's, so remember this is defined as follows, right. So yi is q naught plus qa into xai plus qb into xbi and so on. That is from the definition of yi, right. So if I separate those terms out, so this is 1 by 4 into sigma q naught across all the 4 terms, and again we will just be a little bit right. So qa gets extracted out, then xai is what is remember remaining, and then it is 1 by 4 qb, so on. So what happens to this expression? The sum of all ai's along a column is 0, all bi's 0, aa b are 0, so everything except the first term goes to 0, right. That is what we saw in the previous thing, right. So this is sigma xbi. So all these 3 terms will go to 0 when summed up together. So therefore I have just q naught repeated 4 times, so therefore mean is q naught. That is how we derived the q naught expression. Okay, questions? fair enough. Okay, so now we wanted to get that SST expression, right? So SST is the total variation, which is simply yi minus y bar whole squared I equals 1 to 4, and since we just now did y naught equals y bar equals q naught, therefore this is nothing but an expression that looks like this: qa into xai plus qb into xbi plus qab xai xbi whole squared, right. So this is basically a plus b plus c whole squared. Now you remember your long this difficult formula. So this is nothing but a squared plus b squared plus c squared plus all the product terms, right, 2ab 2bc. Okay. So applying that, you basically have qa squared plus qb squared into xbi squared and so on, right, then plus qa squared b plus xa squared b, all that stuff, right. And then we will write one term, so plus 2 into I equals 1 4 qa into xai into, so b, right, so that is qb into xbi, right, that is one of those terms, other terms I am not expanding. So basically squares plus the corresponding product terms. So how does this simplify now? qa squared, so qa squared comes out and xa squared is simply 4, we saw that, right. So 4 qa squared plus 4 qb squared plus 4 qab whole squared. That is the first 3 terms, right, from the a squared plus b squared plus c squared you get these qa squared into 4 plus qb squared into 4 and so on. Then the remaining dot product terms go to 0, right, xai into xbi across all the 4 rows goes to 0. So all the so if there is ai into bi or ai bi, everything goes to 0. So the last 3 product terms are simply 0, and that is what we have. So this is now SSA plus SSAB. That is how you get that expression. So the purpose here is to not fit the values, but to just find out which is more important than the other, which factor affects your system performance more, given that each factor has 2 levels and you have fixed those 2 levels, right. So usually if you have 2 levels only, you pick 2 extremes normally, right, you pick the lowest and the highest and then see whether when going from the lowest to the highest for a particular factor, if it makes more sense, then yes, you would try to see what happens in between, right. Then you will go to the next level of experiments where you will add more levels within that same factor. So from 2 GB to 32 GB, you see that there is a big difference in performance when I go to 32 GB compared to 2 GB. Then you would say, alright, let us look at 4, 8 and 16 and see what is the right spot for us to operate in given cost and other considerations. Okay. So that is the purpose of this particular analysis. Questions? I guess the biggest question is, am I going to cover chapter 20 or not? Because I felt sick, your chapter 20 got pushed to the last second, but it is okay, we will kind of go through this class. So this is for a 2 factor, right. So what if I have 3 factors? 3 factors is 2 levels, so it's still 2 to the power k, so k factors, right. So So if I have 3 factors with 2 levels each, so for example I give you, right, a system which has memory is one factor and there are 2 levels, you know, say 4 MB and 16 MB, and cache like before, which is, you know, 1 KB and 2 KB, followed by number of processors, right. So this is, say, your factor A, this is factor B, this is factor C, and this is either 1 CPU or 2 CPU. So that is your third factor on one factor. So if I give you this, then how do we proceed? As before, the same principle of generating this table with 2 to the power k rows applies, and then you would just have, right. So we will have I am not going to go through the example. So if I give you the values, so this is the column A, column B, right. So in general, if I have k factors, I will have k choose 2 effects, a whole bunch of them, then I will have k choose 3 effects and so on up to k choose k effects. So there are more effects. In the previous case there was A, B and A, B, those are 3 effects we are interested in. And I go to, right, then you have A and B, how do they interact with each other, and how do A and C interact with each other, then finally A, B, C all together, how they interact with each other. So it sort of nicely falls into place, right. So this is simply your, so if I do k choose 2, I have 3 combinations, right, 3 possible combinations. Therefore AB is a column, AC is another column, BC is another column, ABC is the third column, last column. So I have total of 7 effects. Now my SST will equal SSA plus SSB plus SSC and so on. The same calculation that we did before is going to apply here. And then remember, with the last column, you know, we usually use Y. So the way we would fill up this column is, normally if I look at my binary, we said, right, it is 0 0 1 and so on. Here it is the, so we will keep the last row constant or the last column constant. This one will change every 2 rows and this one changes every other row. That's all. So once I get this, then it's exactly, then everything else is the same. So the value for I, right, so again remember to do the total, the column wise dot product total. So I into Y will give you my Q naught, then the column A into Y, right, A dot Y divided by 4 will give me my QA and so on. So same steps as before, nothing complicated. So I dot Y divided by 4 will be Q naught. QA will be column A dot Y divided by 4 and so on. QABC will be that ABC column into 4 divided by, into Y divided by, or sorry, dot product of Y divided by 4. And then your SST has more factors, SSA plus SSB plus SSC, individual factors, then combination factors, rest of the analysis is ditto. So if you know how to do 2, you should be able to do 3 in the final, you should not stare and say, okay. So that's, and if you really want, I have posted sample set of exercises on the web today, which one of them includes, there is only one question in this whole chapter 17.1, which is basically 3 effects, and you can try that out. Okay. So this is the end of chapter 17. So as per my schedule, I was supposed to go to single factor, one factor analysis, where I have set of qualitative variations, so different CPU types for example, right. So if I give you experiments with only one factor, put it at several levels, right. So that's, but the several levels, whatever, 10 levels, 15 levels, say 10 different CPUs have been investigated, then what is the relative. So what there we want to find out is, right, how much of the variation is because of the difference in the different factor levels and how much of it is because of errors, right. So you want to make sure that, so your SST is simply two factors, one is two components, one is SSA, which is the varied factor, right, that the CPU type that is being varied, and whether there is experimental error also that comes into the picture. So there are only SST equals SSA plus SSE, that is about it. I am not going to go through chapter 20 to break the suspense. Yeah.
It should be, denominator should be divided by 8.
Did I say 4? Yeah, sorry, everything is 8. And SSA will be 2 cubed 2 to the power 3, that is why I wrote as 2 squared last time. SSA will be 2 to the power 3, but your QA will be squared, it will be 2 to the power 3 into QA squared plus 2 to the power 3 into QB squared, right. Your QAs do not cube, only the two factors, K factor will come into the play. Okay, so chapter 20 I am skipping because it is little bit late to start on a chapter 2 days before the final exam. But so what instead what I am going to do is I will just continue with some of the variations. Whatever I talk about, whether that will be on the final or not, I will announce at the end of the discussion. For now, just listen. Yes.
Can it be like what we have done, 3 factors with 2 levels? So can it be a mixture also, like 3 factors with 2 and 1 with 3? So those combinations also.
That what we have to take the general 2k form to a formulation, and from that you can derive. Yes, I mean experimentally we might have different levels for different factors. If they are all the same, then you have this sort of analysis. If it is, yeah.
We can multiply each factor and then that is full factorial.
But your question was if we have different levels in each, right?
Then what will we do? Like here we are saying 2 cubed.
Okay. Yeah. So in that case you will still have the full factorial design, but whether you have this sort of nice analysis when you have different levels, nah, not.
Like if processor is 1, 2 and 3.
Yeah, you can design the set of experiments. This kind of analysis we will have to go back and check. Yeah, I have not done that. Okay. So some things that are useful to know, right? The first variation is what happens if I have 2 to the power k tests, right, or designs experiment types, but I run each of them for R replications, right? That is the extension. So if I, right, so 2 to the power k, but each, that is what we have been training you, right, to run multiple replications. So if I run replications, how does my analysis change, right? So with replications there are only couple of changes to the analysis. Your so what we will have is, right, so AB like before, right, let us say only 2 levels we are looking at, so -1 -1 -1 1. Right. So in this Y column, right, so what I will have is I will have R experiments, results of R such experiments, right. I will have R values for every row, that is all I will have, right. So my Y will simply be the average of those values, then everything else proceeds as before, there is no change. So for example if this is 15, this is 18 and this is 21, I did say R equals 3, right. So I will simply take the average of the 3 and that becomes my Y, that is all. This is 18, right. So we will repeat like I did last time, replacing Y with the corresponding averages across all the replications, and then of course this later on goes into confidence intervals and so on, right. There is a lot more here, we are only scratching the surface, but now the will depend upon the
actual sample taken actually
doing R replications. The standard deviation of those R replication may also depend on these factors.
But where are we using the the actual computation of the SSTs here, yeah, I'll come to that. So what we will have is for right, you will have a set of EIJ, right, for the ith combination and the jth trial, right. So that is what your EIJ would be. Let me put this EIJ precisely. right. So I is the row and R or J is the replication number. Where J goes from, if we say so here now Yij becomes so in each case Eij, right, is actually defined as Yij, which is the actual measured value, minus what you have been what's been computed. So this actually will correspond to Yi, Yi bar, the average value of Yi, right, this will be a Yi bar. So this is the error term for every replication you are computing this error term. So just and then so the if you look at it, the because this is the average, right. So what will happen is the summation of all the errors in a particular row will go to 0. So summation of all the errors Eij sigma Ij across all Ij will go to 0. Then what we are interested in is this so called SSE, which is simply this, right, across all rows and across all replications. So if I give the table, you will compute the SSE, and then your SST now, again you are not getting into the details, is got this extra component SSA plus SSB. So the total variation is actually across all the samples, right. SST is now considering all the replications that you have taken. So the purpose of taking this next to this step is that to find out whether SSE is small or not. If SSE is negligibly small, so I do the same analysis like before, right. If SSE is very large, let us say SSE is 70% of the total variation is because of errors, that means that between replications you have several, right, there is a lot of variation in the replication result for a given combination. Therefore you can say that SSE is very large, that means there is most of the variation is because of experimental errors, you cannot really conclude anything in terms of AB or AB. Ideally you would want to see A and B having good values, or maybe even A, B having larger value, but SSE should pretty much go to something close to 0, 1%, 2% is acceptable. But if SSE is very large, then you let us simply come and report that whatever I am seeing here in terms of variation is simply because of the experimental errors, and that sometimes that is the case, you sometimes run experiments even for CPU measurements, the same job, same computation on the same system at different points in time, even if there is no other background processing and things like that, background jobs running in the system, sometimes you will find that the actual measurements end up being quite varied, either with the granularity is not correct or some other system CPU process kicked in just at the time that you are trying to do, whatever it is, right, or if it is something like sensors from measuring, say values for a sensor, you will find that there is so much variation. So the purpose of this is to do, if I do replications, then I want to ensure that enough replications are there such that my SSE goes to a small value. If SSE is very large, then your experiments are basically inconclusive, because you can't really say that that this particular factor A has any better impact than some other factor B. Okay, so that is just the highlight of there is a lot more in that chapter, it keeps going. And then we will just look at one example of 2k minus p, and after that will be 19, right. So for more details, chapter 18. So in chapter 19 is what some of you asked earlier, right? How do I get this 2 to the power k minus p, right? That fractional factorial design, right? Which means that I don't want to do 2 to the power k, that is too many, and I want to do something less than it. So how do I do that? Okay. So that again, I'll just first section I'll just briefly mention what's going on here, right? So let's say k equals 4, right? There are four factors a, b, c and d, but I only want to do I want a 2 to the power 3 design, right? Not 2 to the power 4. So basic, yeah, so I only want 8 instead of 16. So what is a good combination for that, right? So there are different ways suggested. One of them is you first of all find out which 3 are crucial. You decide that 3 of those factors have to be repeated in all the combinations, but the fourth one only in some variations. I shouldn't have p equals, right, 1 consistently, but I can have something else. So the way we, let's say a, b, c are the selected factors and d is the one that is not of interest. So we will go ahead and write a, b, c, a, c. So we will have our right columns as before. This is my 2 to the power 3 design, right? So I have everything as before. So what do we do now? So I have a, b, c, right? So if I want to bring in d, so again if you look at it, this is minus 1, minus 1, minus 1, right? This is minus 1 and this we said is 1, minus 1 and so on, right? So this is 1 and the ABC column will look something like this. I will not minus 1, 1, minus 1, minus 1, then 1. So you can pick. So what happens is you have ABC, let's say you are keen on, right? So you want to know the individual impact of these factors, but you have 4 other columns to choose from. So this one will tell you interaction between A and B or A, B and C and so on. So you simply choose any one of them. So that would be your, you can replace that and then of course we can go on into
what is the intuition behind why are we actually doing this? Why do we leave one and then take it out later?
No. I don't have an answer for that right now. I have not even tried this out. So when I conduct experiments, I'm going to, this is the combinations of, right? So you will be conducting experiments with A, B, C and D with these 4 different levels, right? So that is taken. As to why this versus something else, and so all I want to do is to create a set of experiments, right, with the different, with variations in each of those levels, right. So in the case of A, B and C I have essentially done all the combinations that I want, and for those 2 set of combinations I just want to, so what we find here in this case is that, right, yeah, for 4 of those combinations I am testing with D at minus 1, I am not testing with D at 1 for 4 of the combinations, right. Whereas in the case if I had the full factorial I would have the same thing would have been repeated, right, I would have had that extra set. So I am testing for half the combinations of what I would have normally tested with this minus 1 and the other half I am testing with 1. Yeah, and then then you run the experiments and what values of y that you get with this combination will have D's factor also taken into account, right.
So what will be the identity function for that D column? It will be same as minus 1, 1.
Yeah, this will be the column. See, all they are saying is that for, you see, you are trying to create combinations of A, B, C and D, right. So you will have minus 1, so this for the first experiment all these 4 factors will be at level minus 1, whatever that level for corresponding factor of D is, right. Everything else is going to be the same as before, and your y here will depend upon the d value, right. If d is 1 you will get a different result, d is minus 1 you will get a different result. That is why y is d is factored into the value that y that you will see when you get experiment with y, when you measure y. So if I replace some other column in the d, will it make a difference? It will make a difference to the type of experiments you are running, right. So if it is this one, for example, this is 1 1 or 1 minus 1 and so on, right. So that if this were to be d instead of that, then just the levels at which you are experimenting in each case is going to be different for a d.